Great. Yeah. So thanks very much for this opportunity. So that's really a distinct topic. So in my case, I will discuss metallic magnets which feature local 4F-based magnetic moments. Nevertheless, the interaction with conduction electrons will lead to interesting phenomena. So these are materials which are crystallizing on the zirconium nickel aluminum type structure, where we will put rare earth atoms on these locations with the large black dots which form a distorted Kagome lattice. And the first example I will mention is holmium silver germanium, where we recently found the first crystalline realization of a two-dimensional spin ice state. And more recently, we see very interesting coupling to the conduction electrons, which gives rise to interesting Hall and magnetoresistance behaviors. And while here we have a negligible Kondo effect, there is also, of course, a question: what happens if you get to heavy fermion metals or Kondo lattices, where the F electrons are placed on this Kagome lattice? And here we also have some interesting new developments. One is that for the heavy fermion cerium palladium aluminium, we see a broad pressure range where the new microscopic experiments indicate spin liquid behavior, and where we also see indication for quantum criticality. And the last topic of my talk will be a material cerium iridium tin, where we are even having a much higher Kondo interaction. So there we are deep in the intermediate valence regime, and fascinating enough, at temperatures and energies more than 2 orders of magnitude below the characteristic valence fluctuation energy, we see the emergence of antiferromagnetic moments at low temperatures, and that may hint to the competition between magnetic frustration and Kondo singlet formation, and could be an indication of a possible Kondo breakdown in this material class. So before starting with my talk, I'd like to acknowledge the main collaborators. The first topic, holmium silver germanium, was initiated by my former postdoc Kan Shao, who is now at Beihang University, and we got great support by all those people listed here. In particular, I'd like to mention Hua Chen from Colorado State, who did the recent theoretical analysis of our magnetotransport data. Then cerium palladium aluminium, that's also a long collaboration, this with Veronika Fritsch and Oliver Stockert. And the new data I'd like to show you were obtained by Mayuk Majumdar, who was also a postdoc in my group and who is now a faculty member in India. And the third topic, this is a quite international collaboration. So there we got the crystals from Japan, from Hiroshima University, Takapatake group. The synchrotron spectroscopy to study the intermediate valence regime was done by Andreas Severing and collaborators. And we got important microscopic insight by Mürzar and neutron scattering by Atrocha from ICES. And my former PhD student, Andreas Wörl, actually did the bulk millikelvin experiments. All right, so the motivation to look for magnetic frustration is, of course, that it supports unconventional states and excitations. And we define this geometrical magnetic frustration as a way to where we cannot fully satisfy all the different pairwise interactions, and that leads to interesting new phenomena. If we just consider classical spins, then we can typically have some constraints which define the ground state and which lead to a multitude of degenerate states at the lowest energy, like in the spin ice cases. And if we also consider quantum mechanical effects, it's getting more interesting, because then many body entanglement and fractionalized excitations may become visible. And so if we then also consider some additional conduction electrons in metallic magnetically frustrated materials, we we can highlight observations like new types of Hall effect, and in the heavy-fermion case, Condor breakdown of fractionalized Fermi liquid. So I like to start with a brief reminder on the physics of spin ice. So in a certain class of pyrochlore-based rarous oxides, we have the magnetic moments placed on the edges of such tetrahedral units, and the single ion anisotropy dictates that the magnetic moments can only be aligned towards the center and outwards the center of the tetrahedra, and the lowest energy are having those 6 out of 16 configurations where always 2 spins pointing inwards and 2 spins pointing outwards, and that's a famous spin ice rule. And there is a residual entropy due to this multiple degenerate configurations, which is clearly visible in the experiments where entropy was collected by was calculated from the specific heat by just integration. And characteristic for these spin ices is that you have, as once you cool them down to very low energies, that there is slow dynamics and freezing, and time scales are getting extremely long. If we consider excitation, so just flipping one spin would result in 2 tetrahedra where the ice rule is violated. So that creates a pair of magnetic monopoles, and this physics of the emergent magnetic monopoles is very fascinating. So we can ask whether such spin ice states would also exist in 2 dimensions. And indeed, we can define something like Kagome spin ice rules, where for the triangular units out of which we built the Kagome lattice, we would always have the rule that either 2 spins are pointing inwards, 1 outwards, or 2 spins pointing outwards and 1 inwards. And there is 4 such possible configurations indicated here, which fulfill this ice rule. And in the Kagome case, now we would have in the ground state always plus or 1 magnetic monopole per triangular unit. Now the theory predicts a series of transitions as we cool down such a Kagome spin ice. So once we first fulfill the ice rule, this separates the ordinary paramagnetic state from the first Kagome spin ice state. But then there is a long range order of the magnetic monopoles in 2 steps before we reach this state here, where now by the blue and red dots, we indicate the charge of the monopole at each center of the triangular unit. So, you know, if you connect the centers of the triangular unit, the Kagome lattice, this gives rise to honeycomb lattice. And this is here the full order of the magnetic charges in this honeycomb lattice of the monopoles that we have in the Kagome spin ice. Now, up to now, experiments on Kagome spin ice were limited to magnetic nanostructures, which are based from ferromagnetic thin films of nanometer-sized region, which has the shape anisotropy dictates that the total magnetization of these films has to point inwards or outwards the triangular units. And of course, it would be nice to have a real crystalline material which features the Kagome spin ice physics. And this was really the major discovery by Kanchao, who found that this physics is realized in holmium silver germanium. The crystal structure of holmium silver germanium is shown here. So it's a layered material where we have these stacks of a distorted Kagome lattice of holmium 3+ ions, and it is an intermetallic compound with a electrical temperature dependence of electrical resistance, which indicates metallic behavior. There is no signature of Kondo scattering, and there is a nice nice degree of fractional perfection, and the residual resistance is as low as 20 microhms centimeter. Holmium in the 3+ state is a non-Kramers ion. It has 10 f electrons, and the total spin orbit coupled moment undergoes the crystallectric field splitting. And in fact, here we have 4 low energy crystal field modes, which are all within 1 milli-electron volt, which is smaller than the RK4Y exchange magnetic coupling, because you see that the magnetic ordering happens at 12 Kelvin, which corresponds to about 1 milli-electron volt. So upon cooling, we see in the magnetic susceptibility several subsequent phase transition, and in the magnetization curve measured at 1.8 Kelvin, this is the black and red data, we see multiple steps and fractionalized magnetization plateaus. So as you see, the saturated state at low temperature has a magnetic moment of 6 μ, and we have a first pronounced plateau at 1/3 and a second pronounced plateau at 2/3, and there is also a smaller plateau at 1/6 and another plateau at 5/6. And these plateaus are separated by the sharp metamagnetic transitions. There's a little hysteresis seen between up and down in the magnetization between the position of these metamagnetic transitions, but there is no hysteresis in the value of the magnetization at the plateau, of course. And I should mention that the system has the easy plane anisotropy, and in the following I will always show you data where the field was applied in the plane along the b-axis. Now, thanks to his careful work on the crystal growth over many years with the self-flux method, Khan realized to grow high quality and large single crystals, which we could then use for very detailed magnetic structure investigation by neutron scattering. And here I show you already the outcome of a magnetic structure refinement, which is based actually on more than 500 peaks detected in neutron diffraction. And so let's start with the in this range of the phase diagram below where the magnetic order develops below 12 Kelvin. So these are data taken at 10 Kelvin, and there a partially ordered magnetic state was found as a result of the refinement, where you see that in each triangular unit there is always one spin pointing inwards and one outwards, and the third spin is not yet ordered. And this partially ordered phase has a toroidal moment. It is drawn here in this configuration in the clockwise sense, but of course there will be a second domain where the toroidal moment would point anticlockwise. Then there is additional Bragg peaks appearing below 7 Kelvin, and here is the outcome of the refinement at 4 Kelvin in zero magnetic field, where you now see that now all the magnetic sites participate in the long-range order, and the long-range order can be visualized as such an ordered version of this toroidal order, which is exactly the same as theoretically predicted for the classical Kagome spin ice crown state. And then Khan also did careful measurements in magnetic field and studied the magnetic states in the 1/3, 2/3, and saturated state. And these configurations are shown here. And without going too much detail now in this short talk, I'd like to mention that in all these configurations sketched here, in all these 4 different states, there is always the spin ice rule is fulfilled. So you will see that always 2 spins are pointing inward and 1 outward, or 1 spin pointing inward, 2 pointing outward for each triangular unit. And these different states are twofold degenerate with a similar value of the magnetization. But most interestingly, we see that they yield to different values of the needle resistance and hole conductivity. And that's now new data, which I show you here on the left part of that slide. So we do field sweep here of the magnetization and here of transverse longitudinal resistance and Hall effect at 2 Kelvin once the field increasing and decreasing. And as you see, interestingly, the Hall effect as well as the resistances show different values on these plateau states. So obviously there is this there is an emergent time reversal degeneracy, which is revealed by this magnetotransport experiments. So despite the fact that the magnetization at the 1/3 and 2/3 plateau has similar value, we see different values in the magnetotransport and the Hall data. And Hua Chen helped us to understand this phenomena, and actually he found that this is related to the non-trivial distortion of the Kagome lattice, which we have in our material Helmholtz-Zentrum. Because there is these two different states, which while they have featured the same magnetization and energy, they give rise to different Berry curvature and thus different magnetotransport properties. These two configurations are actually related by a non-trivial operation, which includes a distortion reversal, as indicated here, where the individual triangular units change their distortion, and then a rotation by pi along the b-axis. And so he did a calculation where he just assumed a minimal tight binding, calculated just a minimal tight binding length structure with s electrons on the positions of the Helmholtz sites, and found that indeed these two configurations have a similar, reveal in a similar band structure, but their Berry curvature is distinctly different, so not just having opposite sign for the two different configurations, but with different absolute values. And integration of that then leads to different so-called orbital magnetization and different anomalous Hall effect, as indicated here over the preon zone, and that could explain this difference which we see in this time reversal-like degenerate state in the magnetization, this difference here in the magnetotransport data. So the general relevance of that is that in such structurally distorted magnets, where the distortion reversal is not equivalent to a magnetic space group operation, we can use the anomalous Hall effect to distinguish these different states, which here have oppositorial orders, which have a similar magnetization, and we can reveal this hidden symmetry by the magnetotransport data. All right, so up to now there was negligible condor interaction. Of course, we can ask what happens if we would replace a holmium with the 10 F electrons by a terbium, which has 13 F electrons, so it's a Kramers ion, and which has just one F hole, and you know this one F hole can get unstable, and there is a lot of spin fluctuations going on, and condor effect can lead to drastic changes of electronic structure. So it is natural to compare the holmium-silver germanium with the terbium-silver germanium, which was actually studied also quite some while ago. And about 10 years ago, we studied it in collaboration with Volkanfield's group and found that it has interesting phase diagram, which also consists of several magnetic states, which are separated by metamagnetic transitions. So there is a sequence of different magnetic phases, but there is important differences to the Kagome spin ice case. Namely, none of these orders respect the Kagome spin ice rules, but it's more complex order. And more importantly, there is non-Fermi liquid behavior and field-induced quantum criticality at the edge between two such phases. So that's an example now for such Kagome magnet where the magnetic moments are condor ions. And for condor materials, of course, we know that there is a competition between the long-range magnetic exchange interaction and the on-site condor effect. And this competition leads to interesting behavior and, for instance, quantum criticality. So that's typically visualized in terms of the donut diagram, which just compares this exponential dependence of the condor interaction, exponential dependence with the antiferromagnetic exchange coupling between F electrons and conduction electrons, compared to the J squared dependence of the RKKY interaction, so the indirect exchange coupling via polarization of the conduction electrons. And now for low values of J, as we see here, the RKKY interaction dominates, and we expect the magnetically ordered ground state, while if we enhance J, for instance, by compressing the lattice in the serum case, we strengthen the Kondo interaction, and then we expect that we that we pass the quantum critical point where the magnetic order gets suppressed and we end in a paramagnetic cross. Now, that's not the whole story. There is also, of course, the F electron degrees of freedom, which may change. And so clearly, if the Kondo interaction is very small, we will deal with localized 4F electrons, while if the Kondo interaction is highly dominant, we expect itinerant F electrons. So the F electrons will contribute to the Fermi surface, and therefore this Fermi surface is called large, and that one is small. And now we have different possibilities what may happen near the magnetic quantum critical point. So one proposal is the so-called Kondo breakdown scenario, which would here be trajectory 1, where we would have the transition from a large to a small Fermi surface at exactly the same point where the system is getting magnetically ordered. But we could also think about different scenarios, namely one where we first have a spin density wave instability of the large Fermi surface where the magnetic order sets in. So we would have an anti-ferromagnetic ground state with a large Fermi surface, and then another separation towards here the side with a negligible Kondo interaction where we get a transition to anti-ferromagnetic state with small Fermi surface. Or we may even think about the opposite possibility, namely that the large Fermi surface breaks apart already in the paramagnetic state, and that would leave a very interesting phase, a paramagnetic state with a small Fermi surface. And the idea is that this could only be stabilized if we somehow weaken the Kondo singlet formation by strong quantum fluctuations, as we may induce them, for instance, by geometrical magnetic frustration. And so you can also think about a finite temperature phase diagram where we have a magnetic ordered phase, and you can depress the magnetic order either in these Kondo systems by just enhancing Kondo coupling, or you can also do it as a function of magnetic frustration. And this works, of course, even in the non-metallic case, that frustration is getting stronger and stronger, and you suppress the order, and that results in a spin liquid phase. And so now the combination of these two scenarios in case of geometrically frustrated heavy-fermion systems is really interesting, because this new exotic ground state is predicted.
Sorry,
Yeah.
just a quick clarification. So in this path 2 that you specify, there is an antiferromagnet. Why does it have a large Fermi surface? Wouldn't it have a Fermi surface reconstruction because of the
Now,
ordering?
of course, there is a Fermi surface reconstruction, but it's called large in the sense that the F electrons still contribute. So the F electrons are still itinerant, and therefore we call it large. Yeah.
Okay, thanks.
Yeah, thanks very much. That's a very valid question. Thanks. And yeah, so and so by the help of frustration, the idea is, or the vision is, that we may realize a state which features some kind of spin charge separation, because the charges would be localized. The charges of the 4F electrons would be localized, therefore it's a small Fermi surface, but the spins are fluctuating and forming a spin liquid phase. And that's also called the fractionalized Fermi liquid. And there is a strong hunt for us experimentalists to find materials which may realize such a fractionalized Fermi liquid state, for which also unusual quantum critical behaviors have been predicted. And that's a motivation to look for Kondo lattice metals where the 4F electrons are located on frustrated lattices, and this zirconium nickel aluminum structure type with the perfect triangular units which are connected in a Kagome lattice, although it's distorted, the nearest neighbor coupling is frustrated, and therefore there is a strong motivation to look for Kondo lattice systems of this structure type. And one of the prototype members of this family class is, of course, cerium palladium aluminum, which was studied since more than 25 years. And in particular, the neutron scattering experiments revealed that there is an antiferromagnetic state developing at 2.7 Kelvin, which doesn't involve all the cerium sites. and which leaves one serum site fluctuating, not participating in the long-range order. The order consists of such corrugated antiferromagnetic sheets, which possibly then result in frustration on this middle position. So we have in each plane a quasi-ferromagnetic coupling along this direction, and those spins, it's believed that those spins here do not order because they undergo the geometrical frustration, as indicated here. Now, more recently, we were asking ourselves how we can define actually magnetic frustration in such metallic heavy fermion systems. Because the ordinary frustration parameter which people are using, experimentalists are using for insulating frustrated magnets won't work. So there we typically define as a frustration parameter F the ratio of a Curie-Weiss temperature divided by the actual ordering temperature. And the Curie-Weiss temperature in a insulating frustrated magnets gives us the energy scale of the dominating magnetic exchange. But you know, in case of a condor material, you get already, the condor scattering already leads to a modification of the temperature dependence of magnetic susceptibility. And the Curie-Weiss temperature is often just a measure of decay, and it has nothing to do with the magnetic intersite interaction. So it's not suitable to define some magnetic frustration. But instead, we recognize that at least in this cerium palladium aluminum case, the specific heat looks quite unusual above the magnetic transition, because you see there is a wide temperature range where upon cooling it grows, and this is a range where magnetic fluctuations are getting important. And we also found that actually specific heat is proportional to the temperature derivative of the magnetic susceptibility. And we see that the susceptibility, or here the magnetization, passes a maximum at a temperature Ts, which is much above the ordering temperature. And since the temperature derivative of magnetization equals the field derivative of the entropy, this means that the line of this magnetization maxima actually defines a line where the entropy is maximized. So it's an entropy inflection point, which we see here. And this is and so our idea is that the system, if it wouldn't be geometrically frustrated, would actually form the ordered state at this entropy inflection point, so that Ts would be the true magnetic ordering temperature if it wouldn't be frustrated. And so we can define a new frustration parameter, which is just the ratio of this expected ordering temperature divided by the actual ordering temperature. And if we now apply magnetic fields and follow this frustration parameter, we see that it enormously grows as we enter the series of different antiferromagnetic states by field in this material. And furthermore, we can also follow the evolution with pressure of this entropy accumulation point, and that's shown here out of that study. And we see that this temperature, which is an indicator below which the spin liquid correlations may start, this disappears at a critical pressure which is almost twice as large as the critical pressure for the long-range antiferromagnetic order. So we may, and also we see here as a false color in this phase diagram that the electrical resistance exponent in this intermediate pressure stage is about 1.5. So we see a non-ferroliquid behavior in this pressure region between the two critical pressures for cerium palladium aluminum. And that was motivation to look more carefully now with microscopic probes what happens under pressure in cerium palladium aluminum. And we did with Mayuk this study of the mirrors are under pressure. So first he could confirm that the long-range ordered state disappears below 1.1 gigapascal, while the signature of magnetic frustration is present up to much higher pressures. So the zero field mirrors are spectra were fitted by such a complicated form where the exponent beta, where it deviates from 1, the so-called stretch exponential behavior starts, and that's an indicator in general in geometrically frustrated magnets for the onset of spin liquid correlations. And interestingly, we found that the onset of this stretch exponential behavior agrees very well with the entropy maximum that is detected from the magnetic susceptibility under pressure. So this line defines the onset of our spin-liquid correlations. And then we also tried to look for indications of a non-fermiliquid behavior and quantum criticality in this pressure regime. And we found in the longitudinal field MIRS-R spectra some interesting time over field scaling, as indicated here, which indeed indicates quantum critical behavior, quantum critical scaling in this pressure range between the first and the second critical pressure. So the idea now here is that we have an extended pressure range where spin liquid correlations remain and where we see quantum criticality. And so that may be an indication for this quantum critical spin liquid in such a geometrically frustrated condor lattice. I think I have still about 5 or 10 minutes remaining. So then I would now turn to the third topic, and that would be to ask whether magnetic frustration may even be relevant if we consider the case where TK is very, very large, so where we are well on the right-hand side in Donia's diagram. And this is the case for serum iridium tin, which is again an isostructural sister compound with the serum atoms on this distorted Kagome lattice. But here, according to spectroscopy, we really have a very strong valence fluctuating behavior. So we have as much as 16% 4F0 configuration we see at 60 Kelvin in the synchrotron spectroscopy experiment. So that's a material which is deep in the valence fluctuating regime. And so it was really very surprising for us to observe that when we did thermal expansion experiments, to observe that the thermal expansion coefficient in this material upon cooling actually gets negative at low temperatures. Because a negative sign in serum systems we typically only have within a magnetically ordered regime. You know, the sign of the thermal expansion is related via the Grüneisen relation with the pressure dependence of the characteristic energy scale. And typically for paramagnetic heavy fermions, the sign of alpha is always positive because the Kondo scale is getting enhanced with pressure, and Kondo scale is the dominating scale. So only if we are in a magnetic regime where RK-Ky interaction over the ratio of RK-Ky to TK dominates, only then the sign of thermal expansion could become negative. And that this happens in an intermediate valence system at below 2 Kelvin, while the valence fluctuating temperatures about 500 Kelvin, this really came as a surprise to us. But from the large size of this anomaly, also a metamagnetic anomaly in magnetic field in the magnetostriction, we saw that it really must be intrinsic and not just related to a tiny amount of magnetic impurities or some tiny inhomogeneity. And so we were asking again our collaborators for the MIRS-R, and this time Atrocha did the experiment. He studied the MIRS-R and he confirmed the emergence of antiferromagnetic magnetic correlations at low temperatures in the MIRS-R data, which at low temperature require a fitting with two components, and the component of with the slow fluctuations shows a maximum just at the same temperature where we see our characteristic minimum in the thermal expansion. So that indicates the emergence of antiferromagnetic correlations at 2 Kelvin in this material, which is really 2 orders of magnitude energy lower than the valence fluctuating energy scale of 480 Kelvin in this material. And there is also a related sister material, cerium rhodium tin, where we just replaced iridium by the isoelectronic rhodium. In the rhodium case, the TK is about half of the size, like in the iridium. And in the rhodium case, we can also induce negative thermal expansion under in-plane compression. And we also observed that the in-plane thermal expansion coefficient shows a divergence as if we had a quantum critical point which is tuned by the in-plane uniaxial pressure. And this may be actually the hint that the geometrical frustration, which is of course modified as you apply the pressure in plane, is very important in determining the ground state of this material first. So the remarkable observation and the task for theory, of course, now is also to understand how we could have the such emergence of magnetic moments with antiferromagnetic couplings deep in the intermediate valence regime, where we wouldn't have expected them. And so our preliminary expectation may be that the geometrical frustration competes with the condor singlet formation, and as a result of this competition, some magnetic degrees of freedom are emerging at low energies. All right, so now I should come to the summary. So I discussed 3 different members of this family of 4f electron-based Kagome magnets, which have also conduction electrons, so which are metallic. And in case of Helmholtz-Zentrum germanium, I showed you that the different magnetic phases, which we uncovered by neutron scattering, all fulfill the Kagome ice rule, and that actually the ground state is exactly the same as predicted by theory for the 2D Kagome spin ice. And the magnetotransport data, like indicated here, the anomalous Hall effect, reveals an interesting difference at the magnetic plateau states, which uncovers time reversal like hidden degeneracy. While the condor interaction is negligibly small in case of Helmholtz-Zentrum germanium, we also discussed the condor systems on this structure type. And in cerium palladium aluminium, I showed you evidence for finite regime in the temperature pressure phase diagram, where we have spin liquid correlations proven by Mührs-R, and where we also see quantum critical behavior. So that's a type of quantum critical spin liquid. While for the cerium iridium tin, which is a material located deep in the intermediate valence regime, a condor breakdown may be responsible for the emergence of low energy antiferromagnetic correlations at very low temperatures. All right, so that's essentially the end of my talk, and I'd like to thank you for your attention. Thanks very much.
Thank you, Philipp. Let's thank Philipp for the nice talk. Questions, both from in-house participants and as well as online participants.
I have a question. Do you hear me?
Yeah, please.
Yes, I can hear you.
Okay,
Yeah.
this is Federico Milin from Lausanne.
Nice
Nice talk, Philipp. Sorry if I missed it. Did you measure the specific heat, and did you find the missing entropy as was done earlier in the spin ice? In that Kagome, I'm talking about the first system you.
Yes. So in case of the Helmholtz-Zentrum germanium, we don't have an indication of missing entropy. So we studied let me see whether I could quickly open our paper and show you the specific heat plot. If you just give me a couple of seconds. All right, so this is the specific heat, the different transitions in the specific heat. There is also a broad peak above the magnetic order, and then there is distinct signatures at the 2 transitions. And we calculated the entropy, and I don't think we have I mean, of course, there is some uncertainty due to the phonon subtraction, but it doesn't seem that a substantial fraction, at least on this scale, which is enormous, RLN 17, that a large amount of entropy is missing. I mean, one has to be in mind, these are large spin orbit coupled moments. We have the crystal field splitting, and as I mentioned, only the 4 lowest singlets contribute to the magnetic order. So we have, I think, R log 4 collected at Tn, and we need to measure up to much higher temperature to collect the full magnetic entropy. But I think we don't have clear indication for some missing entropy in this case. Although it's difficult to see because we have this large amount of total magnetic entropy available from the 10 4f electrons.
Okay, thank you.
Okay, more questions online and people here? So I have a short question about the last part, the cerium iridium compound. So so maybe I missed, but how two-dimensional is the electronic physics of these materials, or?
Well, the metallic behavior is quite three-dimensional. Of course, there is some anisotropy in the electrical resistance, but it's moderate, I would say. So it's not even factor 2. So we couldn't call them 2D. The electronic structure certainly is not two-dimensional.
Okay.
So it's the magnetic moments which are placed on a lattice side, which is geometrically frustrated. And of course, now in the condor systems, you have your F moments on this side. And that's the idea that this geometrical frustration may counteract the condor singlet formation.
Thanks. Yeah, one more question here.
About the holmium compound, I guess if you go below 1 Kelvin, you should be seeing some effect of nuclear spins, right? Do you see something like that?
We haven't seen yet we didn't measure specific heat at millikelvin temperature, so we didn't study nuclear contributions.
But if you go below 1 Kelvin, I think it's already in the hyperfine energy scale.
Yeah, possibly. What we see, what I didn't mention yet, is that there is also a C-axis component of the magnetic moments, and this orders at about 1 Kelvin or so, 1.5 Kelvin. So there is another order which doesn't influence the in-plane Kagome spin-ice structure, which I showed you, but which involves the C-axis component. That's still ongoing. But it will be interesting, as you mentioned, to also see the potential coupling with the nuclear moments. So this we didn't investigate so far. Yeah, thanks very much.
Are there more questions from people here online? Okay. If not, let's thank Philipp once more for the nice talk.
Thanks very much.
Thanks, Philipp.